and tough. You know, so I can make this hard like a knife. But if you have a knife at home, a kitchen knife or a cleaver or something like that, it's very hard, but if you throw it on the floor, it's not going to break, right? And that's a behavior of materials that's really unusual. And steel, because it can behave that way, and it's so cheap, that's why it's an amazing thing. And if you could make a material that could be as tough and as hard as steel for the same price or cheaper, you would be the richest person on earth instantly, more than Gates and Bezos and Carlos Slim and whoever else you want. So that's the amazing thing about steel. So this steel, and you may not have seen this yet in class, but iron atoms at room temperature want to arrange themselves in a cube. So what that means is there's an iron atom at the corner of every cube. And actually at room temperature, there's also an iron atom at the center of the cube. And this crystal is called BCC. Does anyone know what BCC stands for? Wow. It stands for
Body centered cubic.
body centered cubic. Because there's an atom at the center of the cube, right? It's centered on the bottom. This is, when the steel is in this formation at room temperature, it's as soft as it can be. So I can take this bar, this is from the factory, it was rolled hot, they put it on the ground in a giant mountain of other hot bars, and it cooled really, really slow. And when things cool really slow, they go towards the structure that is normal at room temperature. And the behavior of steel in this form is really deformable, right? So this is good because it's plastic, but this isn't very good behavior for a knife, right? You don't want your knives to bend. Something that's this soft can't be sharpened really, or if you did sharpen it and you cut, you took your cleaver and you hit a bone, it would immediately deform. If I take this and heat it up at high temperature, the atoms want to rearrange themselves into a different shape. It's still a cube, but rather than being body-centered cubic, you have a cubic structure with atoms at every corner, iron atoms. And then you have also iron atoms at every face. So this is FCC. This is face-centered. And this is the high temperature crystal structure. So you heat it up, the atoms rearrange themselves this way. You cool it down slowly, they rearrange themselves this way. And then what I'm going to do, so if I heat this up and let it cool down, it's going to be soft again. It's going to behave the same way it behaved before. If I take it this hot and I quench it in water and cool it down really fast, there isn't enough time for the atoms to move back to the structure they want to be in at room temperature, and they go into a different crystal structure, which I'll show you in a minute. Now the other cool thing about this transformation is that this is magnetic. This is not. So I can tell with my magnet here, see how it sticks there? I can tell I've transformed because this won't stick, but right there it will. So right here it's BCC, and right there it's FCC. That's why stainless refrigerators, washing machines, dishwashers, we try to put a magnet on it and it doesn't stick. Stainless steel has nickel atoms in it, and the nickel atoms make the iron want to have this structure at room temperature. this structure is not magnetic. So I'm going to take this now and quench it and cool it off. And this is now cold. And what happens, because I didn't give it enough time to go back, is I get now a third crystal structure. That is sort of a mix of these two things. It's no longer cubic. It's longer. It's rectangular in cross section. And this is called BCT, body center tetragonal. This is a tetragon. And this crystal structure is really stressed because it's stretched and it's very, very hard. So right now, by the way, this is called ferrite. This is austenite. And this is martensite. So martensite is as hard but as brittle as can be. So see how brittle that is? Very easily broken. So this wouldn't be good for a tool, a chisel, a knife, because if you drop that on the floor, and I've done it, it'll break. So what you need to do, and this is sort of the magic of steel, is if I take this crystal structure and I heat it up again a little bit, what you do is you relieve some of the stress. You start to drive the crystal structure back towards BCC and make it softer. So I can, depending on the temperature I heat it to and the length of time that I heat it, I can make this steel behave in any way between this whole spectrum of behavior. I can make it as hard as I want, I can make it as soft as I want, or I can make it anywhere in between. And I can pick a spot where it's going to be hard enough, but also gets tougher and won't break. That's called tempering. And that's what I'm doing right now, just by heating it up. And the structure is still going to be martensite. It's still going to be this body-centered tetragonal. But it is, it's called tempered martensite. And it's a balance of hardness and toughness. So I want to get this to be like just barely visibly red. And that's sort of the heat that gets me to a good balance of hardness and toughness. And then I'll quench it again. And then I'll bend this one because when the toughness increases, it takes a lot of energy to break it. And if it does break, you know, I've sent people flying before when I let them do it themselves. So
When you see blacksmiths working on iron, they're heating and working and then quenching and then where are they in your process?
So most blacksmith stuff like this has almost no carbon in it. And the hardenability, I didn't get into it because it's a little bit much, but the ability of the steel to get hard is a function of the carbon. So with the material they're using and that we use for the most part, you can quench them and they don't get hard. They don't actually, they form austenite, but they don't form martensite. So they aren't hardenable. And you can quench them all they want, and in theory it shouldn't get hard. Now with modern steels being so recycled, they're not so great, and they actually do harden a bit, but nothing like this. So when we do make something like a chisel or a knife, or we make a lot of our own tools like this, we have to use a tool steel with enough carbon in it that you can harden. Yeah, so see how, I don't know if you can see up there, that's glowing red, just barely in the shade. So that's a good temper. So now, if I did this right, it shouldn't even really bend where I hardened it and tempered it. It should bend somewhere up here where I never hardened it and it's still BCC. If I didn't temper it enough, it'll break. So this is more of a test of how good am I rather than, yeah, so see where it's bending? This is all tempered martensite now. So it's hard and it's tough. It doesn't want to break, it doesn't want to bend. And it's bending up here where it's still BCC.
Yeah.
So this is sort of the magic of steel, and you can make it do this. And to me, it's also what's cool about material science is that if I understand the way the material behaves at different temperatures, and I can control that, I can make a material behave the way I want it to behave. The flip side of that is if I know this stuff, and I want to make a new material that has totally new properties or better properties, I can start designing those materials with this knowledge and know, oh, if I want something to be super hard and tempered,